Welcome to the deep dive. Today we're getting into the really fascinating world of landforms, all those different shapes on the Earth's surface. And we're looking at the forces that are, well, constantly changing them.
Exactly. It's like the planet's own sculpting process, happening all the time. We'll be digging into the main geomorphic agents running water, ice, wind, that sort of thing. Our sources today are mainly a physical geography text and its glossary.
Right. And our mission really is to get a handle on how these agents running water, groundwater, glaciers, waves, and wind actually work, how they erode stuff, how they deposit stuff, and how they create the landscapes we see. We'll even touch on how whole landscapes evolve over, well, immense timescales.
Sounds good.
Okay, so let's dive right in. First up, running water. I mean, we see it everywhere. How does it actually shape the land? How do valleys form and, change? And what are the clues it leaves behind?
Well, running water is absolutely fundamental, especially in humid places with lots of rain. You can think of its work in two main ways. There's overland flow, which is water moving kind of like a sheet across the surface.
Like after a big downpour on a field.
Exactly like that. And that sheet flow, even though it might not look powerful, it starts picking up loose bits of soil and rock. That's sheet erosion. This often leads to tiny channels, rills.
Rills, okay.
And as more water flows, those rills get deeper and wider, becoming gullies. Over long, long periods, these gullies connect and carve deeper, eventually forming valleys. So it starts small.
From a sheet to rills to gullies to valleys. Wow. So what about those different stages you hear about? Youth, maturity, old age?
Right, that's a useful way to think about landscape evolution under running water. In the youth stage, the landscape is, well, just starting to be carved. You typically have fewer streams, and they aren't well connected yet. The valleys are usually narrow, steep-sided V-shapes, think sharp cuts. And the areas between the valleys, the divides, are often wide and flat, maybe even swampy. You might also see waterfalls or rapid signs of the river actively cutting downwards.
So lots of energy, cutting down fast. What happens in the mature stage?
As things mature, you get a much denser network of streams, really well integrated like a proper drainage system. The valleys are still V-shaped but deeper, and the main rivers start carving out wider flat areas next to them. Those are the floodplains.
Ah, floodplains.
And those wide, flat divides from the youth stage, they get eroded too, becoming much narrower, sharper ridges. The waterfalls and rapids tend to disappear as the river smooths out its profile.
Makes sense. It's becoming more established. So what about old age? Does everything just stop?
Not stop, but it slows right down. In the old stage, you have fewer streams again, and they flow very gently. The main rivers meander, winding back and forth across really wide floodplains.
Like lazy rivers.
Pretty much. You see features like natural levees, which are low ridges along the banks built up by flood deposits, and oxbow lakes, those curved lakes left behind when a meander loop gets cut off. The divides become broad and flat again, and the whole landscape is worn down very close to sea level. The ultimate endpoint, theoretically, is a peneplain, an almost featureless plain.
A peneplain, almost flat. Incredible. Now, you mentioned valleys,
Yeah.
gorges, and canyons. Are they the same thing?
They're related but distinct. A gorge is typically very deep and narrow with steep, almost vertical sides. It's often formed in hard, resistant rock. Think of it like a deep slot. The Kaveri River Gorge is a good example.
Okay, narrow and steep.
A canyon, like the Grand Canyon formed by the Colorado River, is also deep with steep sides, but the sides are often stepped, like a staircase. And crucially, a canyon is usually much wider at the top than at the bottom. This often happens when rivers cut through layers of rock with different hardness. So you could say a canyon is a specific type of gorge, often formed in horizontally bedded rock.
Got it. Width and those step-like sides are key for canyons.
Yeah.
What about potholes and plunge pools? They sound pretty forceful.
They are. Potholes are circular depressions drilled into the rocky bed of a stream. They form when pebbles and rocks get swirled around by turbulent water, acting like grinders.
Like little drills.
Exactly. And plunge pools are similar but much larger, formed at the base of waterfalls. The sheer force of the falling water, plus the rocks carried with it, just excavates a deep pool at the bottom.
Ouch. Okay, and incised meanders. I thought meanders were for flat plains.
Usually, yes. But sometimes a river that's already meandering starts cutting downwards rapidly. This might happen because the land is being uplifted or sea level drops. The river keeps its winding pattern but carves it deep into the bedrock.
So the curves get locked in stone.
That's a great way to put it. The Colorado River carving through the Colorado Plateau is a classic example. Those huge winding canyons are incised meanders.
Fascinating. And river terraces. Are those like historical markers?
Precisely. Terraces are remnants of former floodplains or valley floors left sitting higher than the current river level. They show you where the river used to flow before it cut down further. If you see matching terraces on both sides of the valley, they're called paired terraces. They're like steps marking the river's history of downcutting.
Like ghost floodplains.
Yeah.
Okay, let's switch to building things up deposition. Alluvial fans and deltas seem like the big ones.
They are major depositional features. Alluvial fans form when a stream flows out from a confined valley onto a flatter, open area, like at the base of mountains. The water spreads out, loses energy, and drops its sediment load, especially the coarser stuff, in a fan shape.
Right, I've seen pictures of those. Like near Amarnath, you mentioned.
Yes, exactly. Their shape can vary a bit with climate, too. Deltas form where a river enters a standing body of water, like a lake or the sea. The river slows dramatically and drops its sediment.
So, similar idea, but into water.
Correct. And tilted deposits tend to be better sorted than alluvial fans. Finer materials get carried further out. As the delta builds, the river often splits into multiple channels called distributaries. The Krishna River Delta is a great example of this branching pattern.
Okay, fans on land, deltas in water. What about floodplains themselves? How are they built?
Floodplains are built layer by layer during floods. When the river overflows its banks, the water spreads out, slows down, and deposits fine sediment like silt and clay across the valley floor. Over many floods, this builds up the flat floodplain surface.
So it's the flooding itself that creates them. And natural levees and point bars, they sound smaller.
They are, and they form right near the channel. Natural levees are low ridges that build up right along the riverbanks during floods. As the water leaves the channel, it drops the heaviest sediment first, creating these natural embankments.
Okay.
Point bars, or meander bars, are deposits of sand and gravel that accumulate on the inside bend of a meander. The water flows slower there, so sediment gets dropped. Think of them as sandy beaches on the inner curve of the river.
Levees on the banks, point bars on the inside curves, and the meanders themselves. How do those wiggles start?
Meanders develop best on very gentle slopes, like floodplains or deltaplains. Even tiny irregularities on the riverbed can cause the flow to swerve slightly. This causes erosion on the outer bank where the water is faster and deposition on the inner bank where it's slower.
And that just gets exaggerated over time.
Exactly. The bends become more and more pronounced. Sometimes a loop gets so big the river cuts straight across the narrow neck of land during a flood, abandoning the old loop, which then becomes an oxbow lake. You see lots of these along rivers like the Burhi-Gandak.
Amazing how water just finds its way and creates all these shapes. Okay, let's go underground now. Groundwater. How does that shape things? What's karst topography and how do caves form?
Groundwater's main game is chemical work, not so much physical erosion like rivers. It excels at dissolving certain types of rock, especially limestone and dolomite, which are made mainly of calcium carbonate.
So it's dissolving the land from below.
In a way, yes. This process of dissolution is key. Where you have widespread limestone or dolomite near the surface, groundwater action creates a very distinctive landscape called karst topography. The name comes from the karst region in the Balkans.
Karst. Okay. What does it look like? What are the erosional features?
You get features like sinkholes, which are depressions on the surface. They can form slowly as rock dissolves underneath, solution sinks, or suddenly if an underground cave roof collapses. Collapse sinks or delenes.
Like giant potholes?
Sort of, yeah, but formed chemically or by collapse. Sometimes you get swallow holes, smaller openings where surface water disappears underground. If sinkholes merge, they can form larger valley sinks or uvalas. And then there's lappies, a really rugged surface with sharp ridges, grooves, and points formed by water dissolving the limestone along joints and cracks. Looks quite chaotic.
Wow. Sounds like a tricky landscape to walk across. And caves, they're formed by this dissolving too.
Absolutely. Rainwater picks up CO2 from the air and soil, becoming slightly acidic. As this water seeps down through cracks in the limestone and flows along bedding planes, the layers in the rock, it slowly dissolves the rock away.
Like carving tunnels underground.
Exactly. Over thousands, even millions of years, this creates complex networks of passages and chambers we call caves. They often form at different levels, following the soluble rock layers.
And inside caves, you get those amazing formations. Stalactites, stalagmites. How do they form? That sounds like deposition.
It is. That's the other side of groundwater's work. Precipitation. The water dripping through the cave roof is rich in dissolved calcium carbonate. When that water enters the cave air, it can release some CO2, causing the calcium carbonate to come out of solution and deposit as solid calcite.
So minerals solidifying out of the water.
Precisely.
Hmm.
Stalactites are the ones that hang down from the ceiling, like mineral icicles, formed drip by drip. Stalagmites grow upwards from the cave floor, usually right below a stalactite, as the drips splash and deposit more calcite.
And sometimes they meet.
Yes. If a stalactite and stalagmite grow long enough to join, they form a pillar or column. It's like slow-motion mineral architecture.
Incredible. Okay, from underground caves to giant rivers of ice. Glaciers. How do these massive ice sheets erode? What do they leave behind? And what about their deposits?
Glaciers are just huge masses of moving ice. You have massive continental ice sheets like Greenland and smaller mountain or valley glaciers like those in the Himalayas, the Gangotri Glacier, for example, which feeds the Bhagirathi River.
And they move slowly, but they're powerful erosional forces.
And immensely powerful. They erode in two main ways. One is plucking, where meltwater seeps into cracks in the bedrock, freezes, expands, and pries loose large blocks of rock, which then get frozen into the base of the glacier and carried away.
Ripping chunks of rock out.
Exactly. The other is abrasion. The rocks embedded in the base and sides of the glacier act like coarse sandpaper, grinding and scraping away at the bedrock underneath as the ice moves. It can smooth, polish, and carve deep grooves.
Plucking in abrasion. So what erosional landforms does this create?
Some really distinctive ones. Cirques are bowl-shaped hollows carved out at the head of a glacial valley, often with a small lake called a tarn, left in them after the ice melts.
Like an armchair shape in the mountain.
That's a common description, yes.
Yeah.
Where several cirques erode back towards each other, they can leave sharp, pyramid-like peaks called horns. The Matterhorn is the classic example. And the sharp ridges between adjacent glacial valleys or cirques are called arêtes.
Jagged peaks and ridges.
Very much so. And the valleys themselves are characteristic, U-shaped. Unlike the V-shape of river valleys, glaciers carve wide, flat bottoms and steep sides. You might also find smaller hanging valleys high up on the sides of the main U-shaped trough, where tributary glaciers join the main one. And if a glacial valley meets the sea and gets flooded after the ice melts, you get a fjord, those deep, steep-sided inlets common in places like Norway or New Zealand.
U-shaped valleys and fjords. Okay, so the glacier carves all this out, carries the debris. What happens when the ice melts and drops it? What depositional features do we see?
The material deposited directly by melting ice is called glacial till. It's a real jumble, unsorted mixture of everything from fine clay to huge boulders, usually with angular edges because it hasn't been tumbled by water much.
Just dumped by the ice.
Pretty much. Meltwater streams flowing from the glacier can sort and round the sediment, depositing it as outwash or glaciofluvial deposits, which are often layered. Moraines are ridges made of till. Terminal moraines mark the furthest point the glacier reached. Lateral moraines form along the sides. Medial moraines form down the middle where two glaciers merge. And ground moraine is the till spread across the landscape as the glacier retreats.
So ridges marking the glacier's edge is an endpoint.
Correct. Eskers are different. They're long, winding ridges made of sand and gravel deposited by meltwater streams flowing within or under the ice, like the fossilized bed of an ice tunnel river.
Wow. Okay.
Outwash plains are broad, flat areas built up by meltwater streams depositing sand and gravel beyond the glacier's end. And drumlins are smooth, elongated, oval-shaped hills made of till shaped by the moving ice. They're blunt endpoints upstream into the ice flow, and the tail points downstream.
Like streamlined little hills. Amazing variety. Okay, let's move to the coastlines. Waves and currents constantly changing things. How do they erode and deposit, and what's the difference between, say, a rocky coast and a low, sandy one?
Coastal processes are super dynamic. Waves breaking on the shore unleash huge amounts of energy, eroding rock and moving sediment. The type of coast makes a big difference.
Let's start with high, rocky coasts, often called submerged coasts, right?
Yes. Often associated with sea level rise or land subsidence, you get irregular coastlines, ground river valleys forming bays, maybe fjords if glaciers were involved. Erosion dominates initially. Waves attack the headlands, carving cliffs. As cliffs retreat, they leave behind a flat surface at their base called a wave-cut platform. The eroded material gets moved around, maybe forming beaches and sheltered spots or bar-submerged ridges of sand offshore. If a bar builds up above water, it's a barrier bar, which might enclose a lagoon. A spit is a sandy ridge attached to land at one end, often growing across a bay entrance.
So erosion first, then deposition starts reshaping things. What about low sedimentary coasts, the emerged ones?
These are often associated with land uplift or sea level fall, or just areas with lots of sediment supply, like near large river deltas. They tend to be smoother, straighter coasts with extensive coastal plains, marshes, lagoons, and barrier islands. Deposition is really the main story here.
Building outwards, not carving inwards.
Exactly. Waves rework the abundant sediment, building beaches, dunes, bars, spits, and barrier islands. Lagoons form behind these barriers and can eventually fill in with sediment to become part of the coastal plain. India's west coast is more like the high, rocky, erosional type, while the east coast is more low, sedimentary, and depositional.
Interesting contrast. Okay, specific erosional features. Cliffs we mentioned. What else?
Sea caves form where waves exploit weaknesses in the rock at the base of a cliff. If a cave cuts right through a headland, it forms a sea arch. When the arch collapses, it leaves behind a pillar of rock standing offshore that's a sea stack.
Like lonely remnants. And depositional features. Beaches, bars, spits.
Right. Beaches are accumulations of sand or pebbles, very dynamic. Dunes can form behind beaches if wind blows the sand inland. Bars are offshore ridges. Barrier bars are emergent ridges protecting lagoons. Spits are attached to land. These features, bars, barriers, beaches, dunes, even mangrove forests, are incredibly important natural defenses against storms.
Natural buffers.
Got it.
Okay, final agent. Wind, especially in deserts. How does wind shape those arid landscapes? What are the key erosional and depositional forms?
Wind is huge in deserts because there's little vegetation, and the dry surfaces heat up fast, creating strong air currents. Wind erodes mainly by deflation lifting and removing loose, fine particles and abrasion, where it uses those particles like sandblasting tools.
Sandblasting, yeah.
But it's not just wind. Occasional intense rainfall causes sheet floods that also do a lot of erosion, even though water is scarce most of the time. So it's a mix.
Right, flash floods are important too. What erosional forms does wind create?
Pediments are common, gently sloping rock surfaces at the base of desert mountains formed by erosion and sleep retreat. If pediments expand and merge as mountains wear down, you get a vast, flat pedoplain, maybe with isolated hills called inselbergs sticking up.
Islands of rock in a flat plain.
Exactly. In basins, you often find playas flat, dried lake beds, sometimes covered in salt. Deflation can scoop out hollows. Abrasion can carve rocks into weird shapes. Mushroom rocks, pedestal rocks where the base gets eroded faster than the top.
Those iconic desert shapes.
Yeah.
And deposition, that means sand dunes, right?
Absolutely. Wind sorts sand very well and deposits it when it speed drops or it hits an obstacle. Dune shapes depend on wind direction, strength, sand supply, and vegetation.
So what are the main types?
Well, you have Bartians, crescent-shaped, horns pointing downwind, formed by moderate, constant winds. Parabolic dunes are also crescent-shaped but reversed, horns pointing upwind, often where vegetation anchors parts of the dune.
Okay, crescents two ways.
Then there are Seif dunes, which are long, linear, often wavy ridges parallel to the main wind direction, possibly formed by slightly shifting winds. Longitudinal dunes are also long ridges parallel to the wind, usually where sand supply is limited. Transverse dunes are long ridges perpendicular to the wind where sand is abundant. And sometimes, with lots of sand, they all merge into complex dune fields, and many dunes migrate, moving with the wind.
A whole zoo of dune shapes. It really is incredible how water, ice, wind, how they sculpt everything we see.
It is, and the key takeaway is that these landscapes are not static. They are constantly changing, constantly evolving. What we see today is just a snapshot in a very, very long movie.
A constantly changing Earth. So we've covered the main agents, how they erode, how they deposit, the landforms they create. But thinking about how dynamic this all is, it makes you wonder, doesn't it? How are we human beings affecting these natural processes? With our cities, our farms, climate change?
That's the crucial question for today, isn't it? Our activities can dramatically speed up erosion in some places, alter sediment flows in rivers and along coasts, change how glaciers behave. We are increasingly a major geomorphic agent ourselves. What the long-term consequences of that will be for the landscapes we depend on, well, that's something we really need to consider.